and also would like to look at the aspects of group delay and what the impact of group delay is going to be. So now we look at the, let me just introduce here itself, group delay. What is the impact of group delay? Okay, group delay by definition we know is tau of omega, which is minus d by d omega of argument h e of j omega. Okay, and please note that this is the true phase or the unwrapped phase, because we cannot use principal value for this. We will get discontinuities and we will get completely erroneous results. So this is either the true phase or the what we call as the unwrapped phase. You have to use that to get the expression that we have. Okay, let me show you the significance of the phase response in a LTI system. Okay, look at the figure on the right hand side. It is a response from you can look at it from the response from 0 to pi. The x-axis goes from 0 to pi, and this is a group delay figure. Somebody has already computed the group delay of an LTI system. So we have an LTI system which has got the following group delay. What is the group delay? You can see that the group delay is mostly around a value of 10 for most of the frequencies closer to 0 and closer to pi. Closer to 0.5 pi, that is pi by 2, you see that the group delay shoots up, becomes very large. Okay, very large. So this is some arbitrary LTI system has got this group delay. Now, why did we not plot from minus pi to 0? Basically, you'll see the relationship is going to be the same. So therefore, we're looking at only the frequencies between 0 to pi. And therefore, summary of this is an LTI system which has got low group delay or constant, almost same group delay for most of the frequencies, and then in a narrow range of frequencies, the group delay has shot up. Okay, so I'm now going to take an input signal. This is x of n. X of n has got two frequencies. It has got a frequency which is omega 1 equal to 0.5 pi and omega 2 equal to 0.25 pi. Okay. Now, how is the input signal generated? You can think of it like this. I have two frequencies. One is a high frequency continuously going from minus infinity to infinity, and I have a low frequency which is okay. So this is what is happening in terms of the two signals. All right. So we have going to apply a window called the Hamming window. The Hamming window. And the reason we apply the Hamming window is to look at only a limited portion of the spectrum. What does the Hamming window look like? The Hamming window with respect to n looks like this. It will basically truncate signals which are outside a certain range. So what we have done is we have applied that Hamming window in the initial portion for the higher frequency, and for the lower frequency we have applied it in the later part. Same window, we have applied the same window. Okay, and anything outside the window, because the window will basically kill it, that's what. So the combination of these two is here. So this is omega 0.5 pi frequency sinusoid. You can see the effect of the window. It starts with a small value, increases, comes down. Similarly, you see. Now, which of these two signals is occurring first? The high frequency one. Okay, high frequency one is occurring first, followed by the low frequency. The low frequency is happening later. Now, if we pass this combination of these two frequencies through the LTI system, remember we can, LTI systems allow superposition. You can take each signal separately and then you can analyze. So what will happen to the high frequency signal? That's the point at which the group delay is maximum. So what that says is this particular portion of frequency, which corresponds to omega equal to 0.5 pi, is going to get delayed by a certain value which is close to 100. Okay. On the other hand, the low frequency signal is going to get delayed by a value which is close to maybe 10, something of the order of 10. So when I pass it through this LTI system, the low frequency signal comes out with a delay of 10, the high frequency signal comes out with a delay of 100. So then what happens? They interchange positions. The first signal to appear is the low frequency signal, and later on you find the high frequency signal is coming through. Now this is the effect of the group delay. So we must understand that a group delay is not, I mean, you may think that, well, some arbitrary quantity is not going to affect. It may actually affect your perception of what the LTI system is doing, because in this particular case, both frequencies are passing through, but one of them is getting delayed more than the other, and therefore you want to be aware of this. Now, on the other hand, had it been a linear phase signal, what would be the answer? Both of them will see the same delay. Whatever sequence in which you applied the input, whatever these frequencies were put at the input, the same sequence will come at the output. Now you see why a linear phase system is actually very desirable, because it has got constant group delay. Okay, so very, very important that we understand that the impact of group delay and what are the effects of that. So this chapter of understanding transform domain analysis requires us to understand subtle truths like this. What is the principal phase with respect to the true phase or the unwrapped phase? What is the effect of group delay? How do I look at it? How do I handle that? So here are some useful tips that we will do. Basically, these are all important results. You can call it thumb rules or things that you should remember. Okay, the first one is a thumb rule regarding the group delay. Rule of thumb. Okay, now we know that the group delay is the derivative of the phase. Okay, now so when will the group delay be large? When there is a large phase change. So that is the first thing that we write down. Okay, so group delay is the derivative of the argument of HEF j omega, derivative of argument of HE of j omega. Okay, so the regions of rapid phase change, that is places where you will see large group delay. These are the ones that contribute to large group delay. Okay, always keep that in mind. Okay, and the importance of this observation is that when do rapid phase change occur? They also occur where there is rapid change of magnitude. Okay, this also corresponds to regions where there is rapid change of magnitude. Rapid change of magnitude. Okay, so here is a good example for us to look at and understand, intuitively what is the impact of group delay. So the first example that we're going to be looking at, okay, is going to be 1 minus z naught z inverse. This is a transfer function which basically says that there is a 0 at a location which is designated as z naught. Okay, So here is a way by which we can understand what this plot is. Okay. Let us say that this 0 is on the unit circle. So this is the location of the 0. Okay, location of the 0. Now, when you look at the behavior of this LTI system, what we are saying is, I want to know what is HE of j omega when omega goes from the range 0 to 2 pi. Basically, I want to go around the unit circle, and at every point I want to know what is the behavior of the LTI system, which is HE of j omega. And this is what it looks like. Okay. Now we can say that at this location, okay, let's call that as theta naught. At theta naught, HE of j omega is going to touch 0. Okay, it's because basically because the 0 is there, the magnitude response will go to 0 at that point. Now, as you go away from that on both sides, you will find that there is a slight increase in the as you go. And similarly, as you go away from theta or further away, what you will find is that there is some change. Okay, so basically the important thing to note is that there has been a change in the magnitude response. When you came close to 0, the magnitude response became very small, and after that it sort of grew to other values. Now, where is the pole for this? If you write down the pole zeros, you have to be careful. 1 minus z naught. So if you write it and in the as a z transfer function, z minus z naught divided by z. There's a pole at the origin. Pole at the origin is sitting here. Now notice that no matter where you are on the unit circle, the pole is going to contribute exactly the same thing. It's going to contribute a value equal to 1 because it's sitting at the origin. Now comes a very interesting way by which we can look at the behavior of the system when the pole is not at the origin, but it is at a location close to the 0. 1 minus z naught z inverse, 1 minus z1 z inverse. Okay, I'm going to ask you to sketch a system which looks like this. On this particular direction, there is a 0 and a pole sitting close by. If you remember, right, see the pole is in the denominator, the 0 is in the numerator. So when you come close to the 0, both of them will look, both of them will be one will be reducing it, the other one will be pushing it up. So except at omega equal to 0. So what you will find in this particular case, the behavior of the system at theta naught, it will still be equal to 0. But at all other points, the pole and 0 will counteract each other. So what you will get is a response that looks like this. Okay, the effect of the 0 is that it will pull it down to 0 in terms of the magnitude response. And the effect of the pole is to cancel, basically to push up the response. And so at all other frequencies, you will find that the pole and 0 are sort of contributing or counteracting each other, except at omega equal to 0, where it forces a 0. Now, what we find is that around theta equal to 0, there is a very rapid change in magnitude. This will be the place where we will also see a very rapid change in phase. That is what we are going to see. So in a nutshell, we look at those regions where there will be a rapid change of phase, and that will usually contribute to places where there is a rapid change in magnitude, and therefore those are the ones that we are always very, very careful about. Now, let me give you one more example for you to think about, because it's very similar to the example that we have studied, but I want you to think about it now in the context of what we have already described as the impact of magnitude change, phase change and group delay change. Now look at this particular figure in the second figure. This says it's the magnitude response of HE of j omega. Okay, so it is the magnitude response. It is plotted on a linear scale. So if you were to plot it on a logarithmic scale, this is what it will look like. So basically, this is what this particular. So it is going to remain flat. It's going to increase around 0.4 pi, gradually increase about 0.4 pi. But so basically on a log scale. So I'm plotting 10 log 10 of magnitude HE of j omega, magnitude response. So there will be you'll see a slight increase and then a rapid decrease, a 0 which is at 0.8 pi. Notice that there is the magnitude response touches the value 0. Okay, it touches the value at 0.8 pi. So this is 0.8 pi. And then slowly increases up to 0.pi. This is pi. Okay, so this is what it looks like. It's a low pass filter. Now, where is the rapid change? The rapid change is happening around 0.4 pi. Okay, that's where it is happening. Okay. Now, what we find is that this will be the place where you will find a large group delay happening. Okay, large group delay will happen there, and so let me see. That's not what it is showing here. The rapid change of magnitude is happening around 0.2 pi. Okay, 0.2 pi, 0.4 pi. Okay, let me. So basically, it is a low pass filter, and if you compute the group delay, this is the group delay that is given to us. It is it's showing that there is a large group delay around 0.2 pi and a smaller group delay around 0.4 pi. Okay, and the input that has been given, just like we saw the last time, Hamming window or output of 3 sinusoids, not 2 sinusoids. So there is omega 1 which is at 0.8 pi, omega 2 which is at 0.2 pi, and omega 3 which is at 0.4 pi. Okay, and now what I want you to do is visualize what we would expect to see at the output. 0.8 pi, there is a 0. That means it is going to completely kill this particular signal. So this signal will not even appear in the output because of the 0 that is sitting here. Okay, so that frequency is completely eliminated. 0.2 pi and 0.4 pi will go through, but notice that 0.2 pi has got a large group delay. Large group delay. So though 0.2 pi occurs in the earlier, in the output it will come later. Omega 2 is equal to 0.2 pi, and omega 3 equal to 0.4 pi appears earlier because of the group delay. So what I want you to visualize is that the whole LTI system, zeros will also play a role. These zeros will eliminate some signals. The group delay can also cause some changes in terms of the behavior of the LTI system, and therefore we must have a good understanding of the magnitude, the phase, and the group delay.